On the left side over here, on the y-axis, you can see depth. Depth is going down. Over here on the x-axis is basically your pressure, but in the form of pound per gallon, equivalent mud weight pressure, basically. So this is the unit that we usually use when we drill a well. PPG, this is the mud weight that we're going to use when the unit that we use to decide the mud weight that we're going to use when drilling. So in this profile over here on the left side, we have the blue lines, the three main lines that we're gonna be focusing on. The blue line is our pore pressure lines. So this pore pressure line, it can be hydrostatic, it can be overpressured like this over here. We're gonna talk about what is hydrostatic, what is normal pressure, what is under pressure later. On the right side, so for example, if our mud weight is lower than this pore pressure, you will start seeing issues related to cake influx, meaning that the fluid from the formation can enter into your well bore. So we would like to prevent that. On the right side, the green color lines, this is the fracture pressure. If the mud weight that we use during drilling exceed this line, you will see tensile fracture. You will see drilling induced tensile fracture. So for example, if you want to do hydraulic fracturing, so this is the line that you need to understand. And the last one over here is lithostatic pressure, basically the overburden pressure, the overlying sediment that we have in the subsurface. Today we're going to focus mainly on the pore pressure side because we're going to talk more about fracture pressure and overburden in our later webinar. But this will form the mud weight window. How much margin do you have to drill? So the smaller the margin, for example over here, then it will be more sensitive, it will be more complicated to drill. For example, you need to use a really specific range of mud weight to drill the well. This mud weight window also not only decide what mud weight you use, it also decide where you put your casing. So basically, you know that this is how much mud weight you're going to put to drill the well. Then you have to isolate this section. Then you put a casing there, and then you drill with higher mud weight. Until some point it cannot take it that mud weight anymore, then you put the casing over there. So it's a basis of the design of the mud weight and also the casing profile as well. But after all, pressure is not just about drilling, so it impacts the whole oil field life cycle. So from exploration up to abandonment. If our pressure understanding is off, our well design could be wrong, our risk could be higher, we lose money, and it's also worth noting that overpressure is not rare. It happens everywhere in all basins globally, so especially deep water, delta system, and what's on. So this is not a niche problem. It's everywhere, and it's good for us to understand it so that we can plan our drilling, our production, and abandonment accordingly as well. So to start with pore pressure, we ask the question, a simple question is, what is pore pressure? So you can see over here in this diagram, pore pressure is basically the pressure of fluids inside a pore. It acts equally in all directions. It pushes against the matrix. For example, in the subsurface, we also have these stresses around subsurface, right? We have vertical stresses, vertical stress, we have horizontal stresses, the maximum and minimum horizontal stress. So you can imagine that the pore pressure over here, it counteracts all these stresses, cancelling each other, and the residual of that is what we call as effective stress. So basically, this effective stress is the stress that the rod needs to take, basically. So, but today what we're going to focus on is the pore pressure side only. When we talk about geomechanics later, we will discuss all these different stresses, vertical stress, the horizontal stress, and what's on. In terms of the pore pressure, there are so many different terms that you might already heard about, the hydrostatic pore pressure, the overpressure, underpressure. So we're going to take a look at that. So hydrostatic pore pressure in a normal situation, or when you have normal compaction, we will have hydrostatic pore pressure. Sometimes people say it as normal pressure. So when you have hydrostatic pressure, it means that the pressure is only controlled by fluid density and depth. You don't need to remember this equation, but it's basically our high school physics, where the hydrostatic pressure is just the pressure of the water column. Basically, it's a function of density, it's a function of gravity, and is a function of the column height. In this case, is the depth itself. So the deeper is the depth, the higher the pressure will be, because it's a function of depth as well, right? So the higher the density of the fluid, for example, fresh water versus saline water or brine, then the higher the pressure would be as well. Most of the time, for fresh water, the hydrostatic pore pressure is around 0.433 psi per foot, and that is equivalent to 0.8.33. So if in your formation you have salt water or brine, then this hydrostatic pore pressure could be higher as well. We always visualize hydrostatic pore pressure in this form. We have depth versus pressure. This is our hydrostatic pore pressure increasing with depth. We also put fracture gradient and lithostatic pressure gradient as well. But at the moment, just focus on this hydrostatic pressure gradient, because it's going to be a reference on how we understand our pressure data. Over here, we have under pressure. Just like how the name suggests, under pressure is basically pressure that is below hydrostatic. Most of the time it happens because of depletion. We produce from the well bore, then the pressure going to drop below hydrostatic. It could happen geologically as well, but most of the time is like temporary. For example, we have a quick fault activities, and then the drainage of the pressure to a certain other part of the reservoir. Then you will see the drop in the pressure under hydrostatic, but over the geological age, it will be in equilibrium and it will go back to hydrostatic basically. So the most common reason of seeing under pressure is depletion itself. Overpressure. Overpressure, as it suggests, is pressure that is higher than this hydrostatic pore pressure. So it could happen when fluid cannot escape fast enough. Common reason for that is probably because under compaction. For example, for our shale, when we have sediments, shale sediment being buried too fast through sedimentation process, then due to the low permeability, the fluid inside the shale cannot escape fast enough, then it will increase the pressure inside the shale. It could also happen due to fluid generation, like fluid expansion, hydrocarbon generation, secondary mechanism when we have high temperature kind of situation. Then this generation of fluid, it can increase the pressure inside the formation, and if that pressure cannot escape from the formation, then it will cause overpressure as well. So this is mostly what a lot of people has interest in, because it dictates how we drill a well quite often. In terms of what we're going to see in the next coming weeks is how we can predict this pore pressure, right? When we do this kind of work, most of the time we start with offset log data analysis. We use our understanding in the offset well, and then we come to some conclusion or some predictive model on what could the pressure be. But one of the biggest part of like validating that model is this validation and calibration. One of the method that we use is we going to refer to the pressure data that we have, our MDT, our RFT. This is direct measurement data. So today, this is our focus, looking at this pressure data, try to understand it, try to analyze it, and see how this data can be used to make the assumption that we are making when we are understanding the offset log data, and trying to come with some prediction on what would be the well, the planned well pore pressure looks like. So today we're going to focus on the direct pressure data analysis basically. So let's start with that, pressure data and analysis. What the origin of pore pressure data? Some of you might be familiar with this already. I saw like we have some drilling engineers, some wildland engineers joining us today as well. Over here, we have kind of like direct measurement and indirect measurement kind of data. So direct measurement is basically a direct measurement that we get from permeable unit, from our sand unit, any permeable unit. Most of the time we don't take it in shale, right? So it could be from different company. They have different names for all of this direct measurement data. We have RFT, MDT, DST, stethoscope. It could be wireline. It could be from your logging while drilling. This is the most reliable form of data. But we also have indirect measurement. For example, kick. If we see kick during drilling, if we see gas or some other drilling response, such as mud pit gain, for example, this is not in direct measurement, but it could give us some level of understanding of what could be the pore pressure. For example, you drill a well with certain mud weight, 9 ppg, for example. At 9 ppg, pound per gallon, you see gas or cake. So it kind of like suggests that your pore pressure is actually higher than your mud weight, because now you see influx. You do not know what is the number, what is basically the pore pressure, because this is not direct measurement, but you know that it could be higher than 9 ppg. While this is less reliable, but it's still a good source of data, because not all the time we have this kind of like direct measurement data due to some reason, probably like the acquisition is not very successful and what's on. So in terms of confidence level as well, as I mentioned, indirect measurement come with lower confidence, direct measurement is high confidence, so we could use it with cautious basically. This is quite important because in the next coming weeks, we are going to take a look at pore pressure. You will see it in PSI sometimes. You will see it in PPG. You will hear the term overpressure, vertical effective. So pore pressure can be visualized in many forms. This is in pressure domain. Standard display of pore pressure is something like this. I'll just bring it to this slide over here. So in terms of standard display pore pressure, it could be in PSI, in MPa. You can see over here at the same part, we are seeing that pressure is increasing. These are all similar data. But when we are looking at it in the term of overpressure, you can see that again, overpressure is the difference between the normal pressure and the actual pressure. Overpressure is constant, although the pressure is increasing. But the difference between this pressure and the hydrostatic is basically constant. When we talk about the vertical effective stress, this is the difference between the pressure and the vertical stress. So in this case, the vertical effective is increasing because both the vertical stress and the pressure is increasing as well. You do not have to bother about this very much because we're going to discuss more on this on the next webinar. And lastly is the mud weight display over here. You can see although our pressure is increasing, our mud weight is decreasing because mud weight is a function of gradient. Basically, the rates of, you can imagine is as a rate of pressure increase. Sometimes pressure is increasing, but the rate is decreasing. That's why you could see that the mud weight gradient is decreasing like this. So it depending on what we are referring to and who we talk to, then we need to have this terminology correct. For example, when you talk to geologists or your reservoir engineer, they prefer to talk in pressure mode, PSI, but when you talk to driller want to know about the PPG, the mud weight, because they are basically designing the mud weight. And again, as I mentioned earlier, this is how our pore pressure fracture gradient looks like. And most of the time when we present this to driller, we present this in PPG rather than in PSI. And I will show you in raw doc how you can do that easily later. All right, we are good in terms of terminology, basically. So here is how we display pressure data. You can see over here, this is the pressure data we get from probably MDT, RFT from the permeable unit. So we know that this could be from sand layer, and sand layer. So to better understand this pressure data, we could put a context. Again, our reference will always be the hydrostatic pore pressure. What would be the pressure be like if the formation is in hydrostatic? We have this information because we know what is the depth, we know what is the density of water, we know, basically that gravity is, acceleration is 1. So if I put my hydrostatic over here, you can see this is my hydrostatic line. I could easily say that this part over here is overpressured because it's higher than hydrostatic. This is overpressured as well with different gradient compared to this one. And this part over here is under pressure, probably because of depletion. We could also introduce this line, which is the fracture pressure line. So again, if our mud weight is higher than the fracture pressure, we will see drilling induced tensile fracture and lithostatic. So because like most of the time, this two lines over here, it give a window to this specific profile that we're looking at. But this week, that is not much of our discussion. So a quick but important reset over here. What we care about over here is, for example, if this pressure is being visualized in bar, MPa, or PSI, if you need to convert it to PPG or gradient, you can use this equation over here. First, for example, if in PSI and this is feet, the gradient is just PSI over feet, right? But if you want to convert it to PPG, pound per gallon, which takes into account the density of the fluid itself, then you can just divide it by 0.052. So how we analyze this kind of data, for example, when we go a little bit into interpretation and we have a connected sense, right? In a connected sense, the fluid is always in equilibrium, meaning that the pressure is being, what do you call it, is being distributed equally. So pressure, it follows like a clean, consistent gradient like this. Typically, it will follow. If it's water, then it follow the water gradient. If it's gas, it follow the gas gradient. And if it's oil, it follows the oil gradient, basically. So one clean line like this, it means we have one continuous pressure system. So for example, if you drill a well in like a typical anticline kind of structure, you would see that here you have oil and here you have water. And if you take measurement in the oil part and you take measurement in the water parts, you will see this kind of data over here. We'll take a look at this in raw dot. So you will have one straight nice line for your oil gradient, and then you will have one straight line for your water gradient. And this gradient, it has its range rule of thumb, like what is water gradient, what is the oil gradient, right? And when you draw the line, the intersection is basically where you have free water level for the oil and water contact. So it could give us some ideas on where basically we have the free water level. And you can compare if your log data, for example, resistivity data, it will kind of like indicate to you, okay, this is where I have the transition between oil and water, and you can confirm that transition basically. Same, if you have two wells in the same reservoir, you might have different data for different wells. And then, for example, over here, I have A, which is this gradient over here for my oil, but because it's still a connected sand, you can see like when I draw the gradient for the B well over here, and it intersect at some points. This intersect is basically where you have free water level, for example. That is the kind of interpretation that you could know. So if you have one well far from one another, you try to understand, is this reservoir is connected and all. Having this well data would be quite useful so that you can see that if it's connected or is being compartmentalized. We're going to take a look at the example of compartmentalization later. So if you have non-connected sands, because sometimes sands are not connected, things change a little bit. So when we have non-connected sands, basically the fluid, it cannot equilibrate properly like when we have clean connected sand. So instead of clean gradient, you will get like steeper gradient, abnormal trend. So this is where we start seeing pressure transition zone. So you can imagine if I have one sand unit over here and then another sand unit over here, and in between kind of like semi-impermeable zone that disconnect between these two sand, you will see this pressure transition zone. More time is easy to detect because the interval gradient is higher than 0.552 psi per feet. Because over the geologic age, it tried to equilibrate between these two reservoirs, but because of the impermeability, then it will have the gradient higher than the fluid gradient, basically. So this will hint to something in between, like it's telling us that something is restricting the flow. Could be compartmentalization or sealing due to like faulting and what's on. example of disconnected sand. For example, over here, I have isolated sand bodies. This could be a case of purge water or like different stack layers of sand for many gas could happen when we have a different pressure regime and what's on. Happen quite often in Gulf of Mexico, offshore Africa, and even around here as well. So you can see I have three different sands over here, A, B, C. They are all at different depth, right? And when we take the pressure reading, the average pressure reading is increasing from 6,000 up to 7,100. So we could easily say that each sand body is behaving independently because the equivalent mud weight over here is increasing as well. So they all have different equivalent mud weight, basically the gradient of the pressure. And we can see the overpressure is increasing as well. So for example, this is my hydrostatic. This is the pressure from each of the points or each of the sand units. You can see that it's not increasing in a constant rate, so meaning that it has its own system, so it doesn't follow the similar pressure gradient anymore. So with that kind of observation, we can make certain conclusion that all of this reservoir is basically isolated. So imagine if you want to drill a well in between B and C over here, you quickly know that probably like you cannot just take the values or the gradient from B and then assume, or A, and assume that the gradient would be similar to what is happening in this the well over here. Probably like if you have another sand, it would be an isolated sand as well. Or if we have another sand that is connected to B, then yes, you can make assumption that it could be in the same gradient with B rather than with C. So this is the kind of like assumption that you would make when you do a predictive work. Let's make it a little bit complicated as well. For example, if you have inclined sand body, they are connected. So in this case, I have A, B, and C. You can see I have pressure data from A, B, and C. You can quickly see that the pressure is increasing from A, B, and C, which makes sense because the depth is increasing as well. But when you look at the equivalent mud weight, it decreases from A to C, which can feel a little bit counterintuitive at first. The key reason is that although the pressure is increasing, it's not increasing as fast as the depth, because all these 3 points, they are within the same connected sand body. So the overpressure stay constant across A to C, but the equivalent mud weight is different. You can see over here, we have a straight line of the overpressure. And if we compare with the hydrostatic, it stays constant throughout. That is suggesting that the pressure regime is connected to one another. It's just like they are with decreasing gradient, basically. And this happens quite often all over the world as well. This is one example in Malay Basin. You can easily see that all of these are different units. They might have different pressure gradient, for example, but over here you could see that there's one. Let me try to use my. Over here, you could see that we have one sand unit, and then it's separated by fault. So each of these could be its own compartment connected to different part of the geology, and then might have different pressure regime. Over here, if we are interested in this part over here, this could be the example of the dipping sand, so that if we predict pore pressure over here, we need to take that into account as well. So it's quite important to understand our geology before we come out with different conclusion. This is where it gets more complicated when we have multi-well plots, multiple grade. But good thing about RockDoc is you can separate this data accordingly. We can filter it accordingly according to the well, which depth it is from, and what's on. So once you do the analysis, when we take it step by step to make sense of it, what you're seeing here is pressure data from multiple wells being plotted together. The color is the color of the wells. And instead of falling on single line, clean line, you can see that the data actually forms several different trends or gradient. Each of this line It represents fluid gradient, its own fluid gradient. For example, this water gradient, another water gradient, and this is oil gradient, and this is probably the gas gradient. So the fact that we are seeing multiple gradients for multiple wells, it could suggest that we are dealing with a system that is not fully equilibrated. So this could be due to multiple aquifers, for example, separate hydrocarbon accumulation, some level of compartmentalization, and what's on. So the key takeaway here is when you see multiple gradient like this, is usually the sign that the subsurface is more complex than just a single continuous system. So go back and take a look at the GIS level of it to see like how far is all of this well from one another and see if there's faulting and what's on. But we're going to take a look at some exercise in RockDoc as well for that. And this is just to highlight to you the pressure transition zone that we talked about earlier. Whenever we have pressure transition zone, we always have sharp transition like this. And then it will follow certain other pressure proper gradient for pressure depending on what the fluid. The example of this is what we have in North Sea. You can see that this is the chalk zone over here. In between two sand layer, this is sand. You can see in the shallower section of the sand, we have what do you call it, hydrostatic pore pressure, normal pressure. At the bottom over here, we have high overpressure, and following a good gradient of probably gas over here. But over here, in between the chart, this is a very high gradient above 0.5 psi per foot. And over here is like up to 0.7 psi per foot. So this is what we would call as pressure transition zone. So for the carbonates there, we understand that it might not follow the sand units up here and down there, but it will follow a pressure transition zone because sometimes because the impermeability is difficult to equilibrate between these two reservoirs up here, then that's why you have a very high gradient for your pore pressure. Example of pressure compartments. This is from Australia, if I'm not wrong. You can see that this is pressure data that is being taken from all these different zones, and they all have different gradient. Quickly, you can see that if I draw a line, they are not going to touch one another because they are all their own pressure regime. So just by looking at this, it's easy to understand that these are all different pressure regime. So for example, for field development plan, right, you could quickly understand that these are all different compartments. If you want to do injection, so your injection will just be limited to this compartment. So for example, if you do CCS project and you want to inject into certain level, so you know that the fluid that you inject, the CO2 that you inject into the formation will not go out from this zone. So your injection limit will be limited as well. So you probably need to have some injection wells in this zone, another injection well in this other zone, and another injection well in this other zone, because they are not connected to one another. So this will decide on the timeline of your injection, how much you can inject, how many wells you're going to put in each zone, for example. So, and for many other applications as well. This is pressure compartments just in one well. So you can see this one well, they go through different formation, different sand unit, and we can quickly see that this is one oil gradient for the unit down here, and another oil gradient and also water gradient for this one unit, and they're not connected to one another at all, meaning that these are two different compartments, not like one sand unit that is talking to one another. So, and lastly, before I go for some demo in RockDoc, this is example of hydrodynamic traps. Happen quite often. Instead of isolated compartments, we have one unit. The reservoir is connected, but the pressure still can vary laterally. Hydrodynamic is a process where overpressure, for example here, you have high overpressure here and low overpressure. It reduces across a reservoir. That this reduction in overpressure, it causes a tilt for your oil water contact. to develop the aquifer kind of hydrocarbon contact in the direction of the low overpressure. It doesn't really affect the gas lake because gas can equilibrate pretty easily, so your gas lake will remain the same. So if you have three wells like this, well A, well B, and well C, you will quickly see that you will have one common gas lake, and then you will have three different gradient for your water lakes. So this still suggests that one connected reservoir is just like it's having different water lake because of the tilted oil water contact. So for example, if you want to drill a well between well A and well B over here, you will see that for your gas lake, the gradient over here, you're fine. You will have the same gradient. You probably can come out with what could be the pore pressure depending on what is the data that you get in well A and well B. Could be equivalent, but for the water part, then it will rate differently. And this is exactly the same example from this study by O'Connor and Swabrick. They see the common gas lake with separate aquifer from hydrodynamic trap, basically. All right, I'm going to move to Rock Dog demo, but before I go to Rock Dog demo, there's datums and units that we could use. In terms of depth, you can use any depth that any units that you are familiar with, kilometers, feet, up to you. The datum, we can change the datum accordingly to TVDSS, TVDKB, TVDML, depend on your operating offshore or onshore. Pressure, you can use bar, PSI, MPa. Same goes to pressure gradient, PSI per foot, PSI bar per meter, bar per foot. And density, you can use ppg, gram per cc, and what's on. Just a quick bonus, like you can screenshot this, or I can pass it to you after this as well, the unit conversion for pore pressure. Where you can convert from gradient to density quickly. For example, 1 psi per foot is 19.25 ppg. What is the gradient at surface condition? And for oil gradient, for example, 20 API oil, what is the normal gradient for oil? 0.4. The heavier oil is at 0.357, for example. And we went through this already, so this is good enough. Let's jump to Rock Dog. Let me just skip this, and you should see my screen. I'll bring up my Rock Dog. So this is Rock Dog. If you haven't seen it, welcome to Rock Dog. It's pretty straightforward. On the interface, you would see all of your wells data on your left side. If you have your seismic data, then it will be here as well. RodDoc has capability to do 1D and 3D work in the same software, so you're not moving from one software to another. But we are just going to focus on the 1D part for the first few weeks. So under each of the wells data, you have your data basically, and it's being folderized accordingly. So all your logs data is under logs. We are just looking at pressure data this week, so we don't really have logs data. And then pressure sets over here. And the fact that it's being folderized like this is some people actually use it as a database, so it's easy for you to find your data accordingly. So for example, if you have MDT data or any other kind of pressure data, it fell under this formation pressure folder. If I open it, you can see here I have for one well, this well, 3007A11Z for the formation pressure. And you can bring in your measurement data like in a very extensive details. So you can see over here, you can not only just put the pressure, but also the type of the pressure. Sometimes you have RFT, MDT, and you want to filter it accordingly. So you can do that later. The quality of the data itself, either is poor, good, fair, so that you can make your decision based on the quality. Also the mobility as well. Like if you want to ignore the low mobility data, you can ignore it later as well. You can see this use button. You can choose which one you want to use, which one you don't want to use. But in the viewer later as well, you can also filter it accordingly. So a lot of clients, they like to use this as a database because then they can visualize all of the pressure data in one viewer, and then they can analyze those data accordingly. In terms of the data that we have, you can see like over here, I have one cluster of data in green color, and I have another cluster down there. Yeah, it is MC well. So let's take a look at this well data, the pressure data, and see how it looks like. I can do that by opening a pressure view. So pressure view is quite exclusive to RockDock. Not many other application has it. A good thing about this is visualize pressure data, and it allow you to interact with it pretty interactively. So under pressure and stress, all the function of like predicting the pore pressure, the building 1D model is under here. We're going to take a look at that in the coming week. But today we're just going to view and analyze the data. I'm just going to open a pressure view that has been set up before. Okay. Okay. It comes on my second. All right, so you can see now you can select what well you want to visualize in this data. So these are all the pressure data that we have brought into RockDock. So, but you can select those data accordingly, like which well you want to visualize. If only one well, then it's only one well. But let's take a look at all of those wells that we have in the system. So here it has colored those well according to the color that we have. If you remember, we only have the green color area and what do you call it, the purple color area. But you can assign different colors to all the well as well. You can see quickly we have some hydrostatic data over here. This is under pressure data. I'm not sure if it's actually good data or not. We'll take a look at that, but we have a lot of overpressure as well. So in RockDock, you can also now, as I mentioned, because you put the metadata or the information there, you can filter the quality of the data. So for example, here, all this data include the invalid, poor, fair, good data. I just want to see good data. So when I click good data, all those data that is questionable is gone. So I can also decide if I want to show only formation pressure data or if I want to see LOT and what's on. I don't really want to see LOT at the moment because we are not doing fracture gradient work. So I'm going to turn them off. It's gone. And accordingly, I just want to see the formation pressure data, my RFT, my MDT. If I want to filter based on mobility, I can also filter based on mobility. Here you say like include mobility higher than 0 point something, but yeah, I'm just gonna ignore this because when we load the data, we do not bring in the mobility information. So in terms of coloring this stuff, it all goes to under legends over here. I can color by wild color just now, but I don't just want the green and purple. I want it to be like one well for its own color. I'm just going to assign auto color the well. So now it's colored by different wells. I can also assign symbol by pressures. Oh no, data type is good. So RFT, MDT, and so on. So I can bring the legend accordingly like this. One great thing about RockDock is the fact that you can play with the unit and also the horizontal axis accordingly. Now we visualize this in pressure, right? But when, as I mentioned, when you talk to a driller, you might want to talk in average gradient, in density, PPG, for example, or some people want to see in average gradient PSI per foot. You can just click this accordingly. It do the calculation on the fly. It doesn't really produce a new log or new data. It's just for visualization right here so that you can analyze it accordingly. I changed it to density. Now it's showing in PPG. So my driller would understand this better as well. I'm going to turn back to pressure. In terms of unit as well, it's quite powerful. I'm showing this in PSI, but if you talk to people in different region, they might want to see it in MPa, for example. So you can change it accordingly. I can also assign secondary unit. So for example, secondary unit, now I have PSI, and they tell me what it is in MPa. Depth, even if it's showing in feet, but you are more familiar with meter, you change it, and then now it has it in meter. If you want to see this in TVDML instead of TVDSS, you can just change it to TVDML like that. So it makes your life a lot easier in terms of like how you look at data and what's on. What else do I want to show you? Pretty much that in terms of like visualizing the data. But let's take a look at one well and how we can see how we can analyze the well. For example, if I choose this well over here, so select none. I want to take a look at only 300711Z. Okay, this well over here, but I want it to be in feet. I want to take a look at this data over here. So for this data, I want to create some gradient for this data. Should be up to 11, something like that. So we can see quickly that we might have one gradient over here and another gradient over here, so that we can decide where is the free water level for the oil water contact. So I can just create a inclusive polygon. And then I can right click on it. For this polygon, I'm going to add best fit. Okay. And over here, RodDoc is telling me that we have all gradient for this well, around 0.176 psi per foot. I'm going to delete this polygon. And I'm going to draw another polygon down here. I'm just doing a rough work over here. Maybe this one. And I'm gonna put another best fit line. You can see this is the water gradient, and it has a contact around this 11.825 feet TVDKB. I can confirm that with my well data, but I think I do not have I do not have data, logs data over here loaded. I'm sorry about that. So basically what you can do, you can bring in your resistivity data next to this viewer and then check how does the resistivity looks like in comparison to this line over here, this free water level over there. So another thing that I could do is I could put more wells to see that we have compartmentalization or not. So for example, just now we have many other wells, right? I'm going to bring 30, sorry, let's take a look at the area over here. I could bring in this 30, the well that we're looking at is this one. I could bring in 30/13.4 and also 27 over here. 2723S, because I know that these have more data. So let's bring in these two well and compare it with the well data that we have over here, the 3007A11Z. And I just show well list. I'm gonna turn on the well that we are interested in, 3013.4 and 23S. Okay. I'm going to remove this polygon as well. Undo zoom so that we see the data better. So you can see that this is the well that we did a little bit of analysis just now. We have another well over here, and we have another well over here. And quickly, even without doing any gradient and what's on, we could easily tell that these are totally like different systems. They could be compartmentalized. It's not like in equilibrium with this system that we have over here. Just to prove that, maybe we can just create a quick polygon again. You can also just create a quick gradient. Let me just create a quick gradient. Maybe I say like here to here is one gradient. And maybe over here, I'm going to do polygon just for the sake of it. This is very rough, so, oh no. I want to create polygon, not gradient. polygon. Maybe here. I think the one at the bottom has a different fluid, so we'll ignore that for now. Okay, so I have an all gradient up here, and we can easily see that, undo all zoom. We can easily see that this is one system, this is another system, and this is another pressure system. So all these three wells, although like it looks quite close to one another in this area, like one is here, one is here, and one is here, they all have their own pressure isolation. So they are not connected to one another. So imagine that if you are drilling a well in between this and this, maybe somewhere over here, then you need to question yourself again, like this pressure measurement data, will it be more represented by this one, the well over here, or the well over here, or none of it, because it's totally isolated system, right? That's why it's important to understand the geology. Take a look at your seismic, talk to your geologist before come out with the prediction of what could be the pore pressure in the next planned well, for example. But it's much more than that. We're going to take a look at how we do a predictive model, for example. But this is the basis of it, trying to understand the measurement data that is available to us and use it to inform our prediction work later. So let me bring in my presentation again. And sorry, I'm using multiple screens. So over here, we are done. So for the next session, I'll do the Q&A after this. But for the next session, this is what we're going to take a look at. The shale pore pressure prediction. This is where we're going to do predictive work using ETEN methods, accumulator method, and what's on. And then we're going to continue with some of the geomechanics and also the 3D work. So let me see if we have any questions. Mikael, is there anything interesting?
I believe that I replied to all questions. In case of any other questions, feel free to send it to Sid, right? And we can.
That's good.
We can answer.
I saw some comments about the audio. It seems like some people say it's okay, so probably like individual issues. Yep. Yeah, if you have more questions, seems like Mikael has covered nearly all the questions pretty well. We don't worry about the recording. Once we have cleaned up the recording and what's on, we're going to share with you. It will be on our website, and I will provide the link to everybody who registered. While we are waiting for more questions, or if there's no question, I just want to highlight some. This is the webinar that we're going to cover. We're going to take a look at all of this algorithm on how we can produce a pore pressure profile. But just know that we do have e-learning access. You can imagine that webinar series is actually being built from total like 6 days kind of training. So it's being compressed into like 5 different webinars. If you're interested to try the software and also to learn more of the theory behind the software, you can have access to our e-learning. Just scan it over there and just register. If you need to talk to us about a specific problem, to request a demo, or if you need to have a session for a specific pore pressure problem or geomechanics problem, you can scan that and also just email us directly. So I guess there's one question coming in. What is the impact of different stresses on pore pressure prediction? So for example, when we talk about vertical stress, right? Vertical stress is the underlying stress of the overlying sediment. So you can imagine that you have your reservoir, and this reservoir, what will decide what is the pressure inside the reservoir? One of the main thing is the vertical stress. This is how much compaction your reservoir will have to experience. The higher the overburden, the more compaction that it will experience. So imagine if in this reservoir, the water cannot be expelled out from the reservoir and the overburden is very high, then you will see very high overpressure. And that's why when we have a deep water and also we have a deeper drilling, that's when you see the overpressure as well. But when we talk about the relationship between stresses and pressure, pore pressure, it could go the other way as well. So for example, if we have a reduction in pore pressure due to depletion or injection, this will change the stress state as well. So it will reduce the stresses when we reduce the pore pressure due to depletion, and will increase the stresses when we increase the pore pressure due to injection. And this has implication towards how we drill a well. Sometimes we will have a narrower mud width window when we have reduction in pore pressure. And also, like when we have injection, that could cause issues related to reactivation of fault and what's on. But these are the topic that we will touch more in the coming webinar. So.
Thanks, Sid, for explaining. I would add one additional comment. So you explained basically the impact of the vertical stress on the generation of overpressure, and as well the changing the stresses due to the injection or depletion. But there is another thing that should be taken into account, which is basically reverse faulting stress regime with a high horizontal stresses, because in all algorithms what we are doing here, we are assessing the vertical compaction on the generation of overpressure. But in case of highly compressional regimes, the impact on the compression is not only through the vertical load but as well through the horizontal load, the tectonic load. And it's something that should be assessed as well. It's tricky, right? Because the vertical stress we can assess the uplift, and how much the rocks were eroded, for instance, during the uplift, or whether we are dealing with the continuous sedimentation is not problematic. But the horizontal stresses change over the geological time, right? So it's not only the current horizontal stresses that we should take into account, but as well the past horizontal stresses. So that's why it's a bit tricky. So to summarize, basically, in the compressional stress regime as well, the horizontal stresses should be taken into account when we are predicting pressure in a shale.
Yep. Thank you, Mikael, for adding on that.
I answered the question. Yeah. I think.
Yeah. Sounds good. Thank you, Mikael. Yeah, the more complicated is your geology, the more complicated the prediction work will become. It goes back to your geology, right? The more complicated the geology, the more complicated for you to get into certain conclusions. So I think we are good with the time at the moment. Thank you for all the good questions that you gave, and a really good session today. Hopefully to see you again in the next 2 weeks. Yes. All right. And in between, if you have any more questions, just contact us. Thank you. Have a good day, everybody.